Hello everyone, welcome back to my channel. Today I am going to talk about degree of freedom analysis of a multi-unit processes. So here is the problem. In this system consists of a mixer, a reactor and a separator, and the chemical reaction taking place is A to B. So we are given the following information. Steam 1, the fresh speed is 100 kg per hour, contain 80% of component A. Stream B, the makeup feed that contains 40% of component A. And then stream 5, the final product contains 95% B. The diagram illustrates the flow stream 1 and stream 2 along with the recycled stream S6 enter the mixture. The mixed stream S3 goes to a reactor and the reactor effluent S4 goes to the separator and the separator splits into the product S5 and recycle S6, that is again come to the mixer. Notice we have several unknown flow rates and composition throughout the system. So now we'll analyze this problem using two different approach. Approach 1 is to analyze the entire system is one overall unit. So we draw a boundary around the entire process. So ignoring the internal stream like recycle stream S6 and intermediate stream S3 and S4. Now here that step B is to count the unknowns that cross the overall system boundary. There are only two external unknown stream, that is M2, that is the makeup feed flow rate, and F5, the final product flow rate. Therefore, number of unknowns for the overall system is 2 because stream 1 information is known here. So here only unknown is M2 and M5. So here so number of unknown is equal to 2. Now overall again that system we have to take that. So step number C is to count the independent equation for the overall system. Since the overall system has two components A and B, we can write two independent material balance. So in the overall mass balance, so mass in equals mass out. You can see, so mass in equal to the mass out. So here stream 1 and stream 2 enter and stream 5 leave. So 100 plus M2 is equal to M5. Another equation 2, component A balance. So mass of A in plus generation of A equals mass of A out plus consumption of A. So however, in that overall system, it is often simpler to track component A and B separately, acknowledging the consumption of A and generation of B inside. So using the total balance equation, 100 times into 0.8 plus M2 times 0.4 equals the mass of A in the final product stream. Since the product stream S5 is 95% of B, so it must be 5% of A. So this equals M5 times 0.05. So we note again that recycle stream S6 is internal, so it doesn't appear in the overall balance equation. So thus the number of independent equation is 2 in that overall system. So now step D is the calculate the degree of freedom. So here NDF will be 2 minus 2, means the degree of freedom is 0. So this confirms that problem is solvable by analyzing the overall system balance alone. The solution involving two linear equations simultaneously. one is 100 plus m2, that is m5, and 80 plus 0.4 m2 is equal to 0.05 into m5 m.5. So from here m2 will be 78.95 kg per hour and m.5 will be 178.95 kg per hour. Now if I analyze degree of freedom unit by unit, so what will happen? So now we look at the approach 2, where we analyze each unit separately to check the degree of freedom for each piece of equipment. The diagram shows the three units. One is mixer, reactor and separator with the stream connecting them. If we analyze each unit individually, the mixer has degree of freedom, that is plus 3, because in mixer 5 unknowns and 2 equations, so degree of freedom will be 5 minus 2, that is 3. For reactor, degree of freedom will be plus 1 because unknown 5 and equation is 4, so degree of freedom actually 1. And separator has degree of freedom, that is 3, so unknown here 6 and equation 3, so degree of freedom is 3. Since none of the individual unit have degree of freedom 0, so this confirms that you can't solve the problem by starting at a single unit. So let's look at the detail count for the mixture. So the unknown crossing the mixer boundary are m2 dot, that is makeup feed rate, m3 and x3 the mixed stream flow rate and composition, and m6 and x6 the recycled stream flow rate and composition. So this gives total 5 unknowns, and the equation available are overall mass balance and component A balance. So this gives the total 2 equation. So degree of freedom for the mixer is 5 minus 2, which is equals to plus 3. Now if I coming to that unit, the reactor, the unknowns are m3 and x3 the inlet flow rate and composition, m4 m.4 x4a and x4b the outlet flow rate and composition. So this gives a total 5 unknowns. So the equation available are more numerous here. So overall mass balance m3 is equal to m4, and two independent component balance with the reaction, one is A and one for B. The conversion here specification is given, so that is xa is equal to 0.70, you can see here. Okay, so this gives a total 4 equation. So here degree of freedom will be 5 minus 4, which is plus 1 or 1 we can say. And then finally we can go to the separator. So here unknown is m4, that x4 to a, x4 b, m5, m6 and x6, 6 unknown. So overall that is material balance m4 m.4 is equal to m.5 plus m.6, component balance a and component b. So we have 3 equation. So here degree of freedom will be 3, 6 minus 3, 3. So here that important notes, if we sum the individual DOF, so 3 plus 1 plus 3 equals 7. So this is not of the degree of freedom of the system, because many of the variables are shared between the units. For example, M3 is unknown for both the mixer and the reactor. Okay. So from here that connecting units, to correctly find the degree of freedom entire multi-unit system using unit by unit approach, we must count all unique unknowns once and count all the variables that is available and independent equation. Here that 9 total unique unknown variables, so like m2 dot, m3 dot, x3, m4 dot, x4 x4b, m.5, m.6, x6. So total number of unknowns will be 9, and total equation, so 2 plus 4 plus 3, so that is 2 from the mixer, 4 from the reactor and 3 from the separator. So we have 9 equation. So total will be, so in the degree of freedom will be 9 minus 9, so that is 0. So both approach confirm that way we can also solve So here both approach confirm that multi-unit process is exactly specified, and that is also solvable. So here I showed you that if you take that overall that flowchart, so from that also you can find the degree of freedom, and if you connect all that unit, so from there also you can easily calculate degree of freedom. So both way we can solve this problem. That's it. Thank you.